Squelching earthquake that occurred on the Enriquillo Fault. Okay, that's all done by historical record. Okay, now you can also go back much longer in time by trenching across the fault. You get a bulldozer, you trench across the fault, and then you can see. You have to be a very perspicacious, careful person looking for this, and you look in the trench for where you think the fault has ruptured before. So here's an example. This is from the eastern Bay Area. This is the Hayward Fault. And then the fault ruptures to the surface at the time, here. So then what happens? Then you have sediment that gets deposited over it. Then you have another rupture. Here it ruptured up to here. Okay? And then you have sediments, or maybe not so many, that are deposited above it. You can date the paleosols, the old soils. You see 9,000-year-old gravel. And it's 4,000-year-old silt here, and you can then date, bracket when the earthquake must have occurred, and then you take the complete length of time, divide it by the number of events, and you get a recurrent interval. So that's something else you can do. Here is just an example where it's been done extensively in Southern California, on the southern San Andreas. You plot it all up, and you can determine what the slip is along the fault per year, what you estimate. Now, this has only been done once. It's been done extensively in Southern California, Northern California along the San Andreas. It's only been done once in the Caribbean. It was done by Carol Prentice of the U.S. Geological Survey along the 7th Knot Fault. Okay? Although it's only been done once, this was very, very important when we went to look at what was going on here, because it gave us an idea of how much slip was occurring on this fault. Okay? So we didn't have to make sure occurred on other faults when we did our model calculations of where the slip was distributed. All right, so the GPS geodetic results, the plates move at centimeters per year, but we need to be able to see the motion. This is an antenna that we use, and we use high-end equipment that has many satellites and all the frequencies. We collect data every 30 seconds for 2 to 3 days. We process using JPL software, the same software they use to track the satellites in orbit. And then we occupy the site the first time, and we return to the exact same spot at some time later and take the measurement. There's a steel pin you can see down here that's epoxied into the rock or tops of buildings, and we return exactly to that spot, okay, and level it until we can get millimeter per year precision in our measurement. This is just the history. We've been doing this. I got involved in 1994. It started in 1986, funded by NASA to look at the Caribbean motion relative to North America. And this is essentially what's been done since 1986. Not important. The data look like this. Each one of these is a 24-hour average of what the position is of the site. And this is years. 1994 to 2002, this is old data. So each one of these is a position. This is a position in latitude, a position in longitude, and a vertical position. Okay? And each one of these dots, then you draw the line to get the velocity. Okay? This is where it is at time 1, where it is at time 2, where it is at time 3. Okay? How much it moves over a given time is the velocity. So this is what we do. We divide it into the latitude component, the longitude component, and a vertical component. These are 2 sites in the Northern Caribbean. This is in Puerto Rico. This is in Virgin Gorda and the British Virgin Islands, just to give you an idea. Okay, so what we did is we modeled what the faults were doing and what the blocks were doing in the plate boundary zone. So this is just the GPS data that we had that showed the velocity. This is velocity relative to North America. So here's North America 6. These are the pieces of the Caribbean that are moving relative to North America. And these are all the pieces that we used, all the motions that we used in the model. Okay? We also used the one piece of information we had for the fault here, which was from Carol Prentice, and we know the fault orientation and geometry. Okay, now this is the most critical part here, how this works. So how does GPS geodesy constrain how the fault behaves? Well, the idea is elastic.